The first video of 2024 is the integral of square root tangent x. So it's an antiderivative problem that I have solved before as part of the solution development for a differential equation. But the solution development I presented there is drastically different from the one I'm going to show you right now. It starts off with defining two auxiliary integrals, a and b. Now a is defined as the integral of square root tangent x plus square root cotangent x dx. And b is defined similarly as the integral of square root tangent x minus the integral of square root cotangent x. And how does this help us get to the target integral? Well, if you add a and b together and multiply the whole thing by 1/2, that yields the target integral. That is the integral of square root tangent x. And if you're interested in the integral of cotangent x, that I'm going to call j or something, for that you just have to take a minus b and multiply it by 1/2. So that's our plan. We're going to take our relatively simple looking integral, and instead of evaluating it directly, we evaluate two relatively more complicated looking integrals, and it turns out that these integrals are much easier to evaluate than the actual target integral. Then we combine the results accordingly to get the integral of square root tangent x or cotangent x, whatever you need. Okay, so we're going to start with integral a here, and we start off by expanding the tangent and cotangent functions. So that means a equals the integral of square root sine x divided by square root cosine x plus square root cosine x divided by square root sine x. And on simplifying the integrand, we get integral sine x plus cosine x divided by square root sine x times cosine x, integration with respect to x, of course. Now, what I need here is a substitution, but the substitution is not immediately clear. But we could use a hint. Whatever substitution we invoke, we'd want the differential element to turn out into sine x plus cosine x times dx. That's what we want our differential element to be. So this is what we know. We know that sine x plus cosine x dx should be du. And that pretty much solves the problem, because on integration, we get sine x turning into a negative cosine x, and we have the cosine x turning into a positive sine x function. So that's the substitution. We let sine x minus cosine x equal u. And that solved the problem for the differential element. But what about the cross term in the denominator, the square root of the denominator? Well, if I square everything, that should give me a cross term on the left-hand side. So I'm going to have the squared sine function plus the squared cosine function minus twice the product of sine and cosine. Terribly sorry about that. And this equals u squared. Now, sine squared plus cosine squared is, of course, always equal to 1. So this implies that 2 sine x cosine x equals 1 minus u squared. And all I need here is a factor of 2. So let me introduce that here and a root 2 out there. So under my substitution, this means that a equals root 2 times the integral of du divided by 1 minus u squared, which we immediately recognize as the inverse sine function. So we have root 2 times the inverse sine of u, and u is defined as sine x minus cosine x. Yep, exactly. So we have root 2 times the inverse sine of sine x minus cosine x plus some constant of integration c. Now for the integral b, we again expand the tangent and cotangent functions and simplify the integrand to give us sine x minus cosine x divided by root sine x cosine x dx. Okay, so again, we'll take a hint from our differential element here. What we need is sine x minus cosine x dx equal to du. And let me introduce a couple of negative signs here. So now on integration, I have sine x turning into a negative cosine x function, and the two negatives cancel out. So I have cosine x, and the cosine function gives us a sine function on integration, and the two negatives again cancel out, giving me cosine x plus sine x equal to u. So that's what the substitution needs to be. And this implies, again, squaring everything to make sure that I get the cross term, we have cosine square x plus sine square x plus 2 sine x, cosine x equal to u squared. Again, this thing is equal to 1, and this means that the cross term here equals u squared minus 1. So again, I need the factor of root 2 here, and this means that b equals negative root 2 times the integral of du divided by root u squared minus 1, which I think is the inverse cosh function, but I'm not sure if I remembered that correctly, so I'm just going to evaluate this completely instead of messing up and then leaving a pinned comment. Anyway, so we're going to let u equal the cosh of phi, which implies that du equals sinh phi d phi. Now, we know that the squared cosh function minus the squared sinh function equals 1. So that means that cosh square phi minus 1 equals sinh squared phi. So looking at this whole structure, yep, b is negative root 2 times phi after all the substitution and integration stuff. And phi is the inverse cosh of u. And u was defined as sine x plus cosine x. So that's what the integral b evaluates to. And of course, we have the constant of integration here as well. But of course, all the constants are going to be absorbed into one big constant of integration when we add up the integrals. So finally, we conclude that the integral of tangent x dx equals 1/2 of the sum of a and b, right? So that means I have root 2 by 2 times, what exactly did I have there? Yeah, it was the inverse sine function, sine x plus minus cosine x rather, then a negative sign here. So I have inverse cosh sine x plus cosine x plus the constant of integration c. And we have a very similar structure. Let me just move this around a bit. And there you go. And for the integral of the cotangent of x, we have root 2 by 2 times inverse sine of sine x minus cosine x plus the inverse cosh of sine x plus cosine x. And that concludes the solution development. I hope you enjoyed the video. Be sure to like and subscribe. Thank you. See you next time.